All right, here we are, example one. So we are going to go ziplining. Let's see, we're going to go from one platform down to another. So it's going to look something like this. We're in the jungle, so it's a tree. Then we're going to another tree on a contraption like this. So there'll be a platform here, and there'll be another platform over here, and then you'll have your line, just like that. And you'll slide down that line, just like this girl's doing. And we want to figure out how much work gravity does to you on the way down. All right, and there are two methods. Well, actually, I said three different ways to do this, but really, I said you can figure out two different ways to do this, and one of them was if you use sort of a parallel distance. That is, we have a force, and that force is going to be gravity coming down, right? So we have a free body diagram like that. Work is coming down. Got some axes doing axis things, Y and Z. And obviously there's some tension in this line that keeps you from going directly downwards, so you're coming this way instead, right? So you're accelerating that way. So we can look at this in a couple of different ways. So we can either look at the work done by this net force here, which is the force component parallel to the zip line, right? Or we can looking at the force downwards, and then we have to think about the distance downwards. So we've got those two ways to look at that. So that sort of means that if I'm going to do both of them, which I am, we have to look at some triangles. So the first one is the easy one. We've got the zip line, right? So we have the zip line there, and it's a triangle. Right? So we have 160 feet on the horizontal axis because there's a crocodile here, just waiting for somebody to fall off. And then there's the 120-foot drop there. And I guess if we're going to have to figure out in one instance where we're looking at this net force, if we're going to look at that in that direction, then we have to know the 200 feet there. Right, so that's one triangle that we have to look at. But the other triangle we have to look at is the other triangle here, where one of these legs is your weight. So you're 150 pounds of weight, or of mass, which means you have 150 pounds of force here. But this triangle is actually a similar triangle to this one. So if this is 150 pounds, then, and this is 200 feet, so these are the hypotenuse. This is the hypotenuse of the zip line, and this is the hypotenuse of gravity. Then this shorter line here has the same ratio to 200 that 120 has, right? So we have 120 is to 200 is equal to what we want over 150. So that's not going to be particularly difficult. If we look at that, that's like 3/5. So if we multiply this one out, we need to multiply this one out for this one. That makes this x 90. So this is 90 pounds in that direction. And the other direction does the same thing. We have 160 to 200. 6 is like the other component to 150. So that makes this guy here, let's say 120 pounds. Okay, but that's the one we don't care about, so that's okay. So that's sort of the setup for this entire problem. We figured out what we're going to have here. We've got one triangle for distances and one triangle for forces, and we'll be able to use those to find the work. And we're going to do it in the two different formulas so that we know how to use each one. Let's use the sort of parallel distance, right? So let's see, parallel. How many L's in parallel? Okay, so that's W is equal to F times D parallel. F is the force of gravity, which is 150 pounds. So that's equal to 150 pounds. Times the distance down. Distance parallel is the same distance, so this way's going down, this one's going down, so we use the same components, 120 feet. Multiply 150 by 120, that is, see, 100 by 12 by 15. 12 by 15 is like 30 by 6. 30 by 6 is like 18,000, I think. 18,000, and the way we usually call this is foot-pounds. SBLEF. So that's 1,800 foot-pounds. Okay, so we have a separate way to do this, which is going to be that parallel force. Now this is the real physical one, right? Because remember the whole deal about our work was it's the amount of force along this path that you're taking, because that's the force that speeds you up or slows you down. Okay, so there's the parallel distance one in this case is easier, but because basically I gave you numbers that were already in that direction, right? The 150 and the 120. But the distance, the one that makes more sense physically, the one that describes what's actually going on, is if I take this distance, which is 200 by this force component, which is 90 pounds of force. But people often use this other one because it's easier, and a lot of people have an easier time with the concepts when you're using trigonometry on real triangles rather than trying to use the vector concepts, which are just a fancy form of trigonometry, at least for the level that you have to use them. It's just a fancy form of trigonometry. There's a level at which they become very, very important, all those vector properties and things like that. But when you're doing the stuff that we give you to get used to them, at that point, really, it's just fancy trigonometry. All right, so now we have 90 times 200, so it's 18,000 again. That's actually an easier... Oops, that's feet. So it is the same answer, right? This guy and this guy are the same. So that seems to work out pretty well. The two different formulas. The work is equal to the force times the distance in the direction of the work, or the direction in the distance in the direction of the force, the parallel distance method, right? This times this is equal to this times this, which is something you probably should expect if you're thinking about it, because what we're doing is we have one projection times the magnitude in the other direction, in the other component. So they're the same sort of thing. They just sort of look a little bit different, and depending on the problem, one will be easier than the other, usually. You could set up the problem so that they're both just as difficult, but you see a lot of people using this parallel distance method because it sort of makes sense intuitively as far as the geometry is concerned. But as far as the physics is concerned, the parallel force method is the one you probably should be using to emphasize the meaning of the work. All right. Well, thank you very much, and I will get another one of these out for you very, very soon. Bye now.